Good morning. This is Shivashankar Rajamani, Associate Professor, Department of ECE, KSA College of Engineering. Today we are going to see about transient analysis. So this is my outline of my transient analysis. First is introduction to transient state and transient response. Then theory in transient, which is growth and decay. Then a single problem to solve it. Current, we are going to find the current and we are going to find the voltage across inductor and resistor when switch is closed, and we are going to again see the voltage across resistor and inductor when again switch is opened. At the given time, what will be the transient response? Then sum up. This is my outline of my presentation. So first is transient state. In a network containing energy storage elements with change in excitation, the current and voltage changes from one state to another state. The behavior of the voltage and current when it is changed from one state to another state is called as transient state. We could able to see an analogy of this thing. Let us take one ice cube from the fridge. When this ice cube is kept outside the fridge, we could able to see that the ice keeps on melting till finally we get full of water. The change from one state, that is ice state, to the water state, in between, is called as transient state. Then we will go for another heading, transient time. The time taken for the circuit to change from one steady state to another steady state is called as transient time. Here the analogy which we already said, the time taken from the ice cube to the fully of all the ice or got melted to become water. The time period in between the time period which is called as transient time. And third is transient response. The energy storage element like inductor and capacitor deliver their energy to the resistor. Hence the response change with time gets saturated from after some time and referred as transient response. So this inductor and capacitor will deliver energy, whereas the resistor will reduce the voltage. So we are going to take an RL transient analysis. Here we have a voltage supply of V and we have a switch which is open, right? We have a resistance and an inductance in series. When the switch is closed, the current I starts flowing through the resistor and inductor, since they both are in series. From the KVL equation, we could able to see that V is the total voltage potential rise, which is equal to summation of all the potential drops. So potential drop here refers to voltage across resistor plus voltage across inductor. And this can be represented in terms of current equation by using Ohm's law. So R into I of t, where t is the transient time. Here it will be continuously changing, so that's why R is changing, I of t, plus L into di by dt, which is equal to voltage. So you take Laplace on both sides. So R into I of s plus, if you differentiate di by dt, if you take Laplace, so it is s into I of s minus I of 0, where I of 0 is the initial energy stored in the inductor, or if it is in the capacitor, it is the value which is already stored in the capacitor, which is multiplied with inductance. If you take Laplace for a constant, so it is voltage divided by S. So I want I of S, So I of s, just take it from the bracket. So it is r plus s into l, which is equal to v divided by s. So I want I of s. So I of s is equal to v divided by s into ls plus r. So I just simplify this for my thing. It is s plus some terminology. So I of s is equal to it's v divided by l whole divided by s into s plus r divided by l. So we can use a divided by s plus b divided by s. If you find the value, so it's for a it is v divided by r, whereas for b it is minus v divided by r. So substitute in the equation. So I of s. So take Laplace on both sides. So I of t is equal to it's v divided by r minus p divided by r into e power minus r divided by l into t. So which is your current. Alright, so we have v by r constant. So we'll take from the bracket. So v by r into 1 minus e power minus r by l into t. So this is the current equation. So it's v divided by r. So it is slowly changing and goes to the steady state. Here the I of t is equal to it's v divided by r, since it is a time constant for inductance and resistance, it is L divided by r. So substitute for t, so which is equal to L divided by r. So the final equation I of t is equal to v divided by r bracket 1 minus e power minus r by l into L by r. So if we simplify this, we will be getting v by r bracket 1 minus e power minus 1. So we already know that e power minus 1 is equal to 0.3678. So v by r it is 1 minus 0.3678. So we will be getting 0.632 v divided by r. The time constant for RL series is defined as a time during which current increases to 63.2 of its steady state value. Then we need to find the voltage at resistor. So VR is equal to Ohm's law. So it's I into R. So it's V by R into 1 minus e power minus R by L into T into R. So R will get cancelled. So it is V into 1 minus e power minus R by L into T. Likewise, transient voltage at inductor. So VL is equal to it's L into di by dt. So differentiate I of t. So V by R is constant. So if you differentiate 1, it is 0. Minus e power minus R by L into t. So you will be getting minus R divided by L. So final equation it is VL is equal to V into e power minus R by L into t. So when you again switch open, the whatever the energy stored in the inductor will start to release through this capacitor, which you call it as decay transient. So at I of 0, which is equal to V divided by 0, which is at time t equal to 0, which is equal to 0. So potential rise here it is 0, so you have only potential drop. So VR plus VL. So R into I of t plus L into di by dt, which is equal to 0. So taking Laplace on both sides. So if you simplify it, so I of s is equal to R divided by Ls plus R. So if you simplify this, so I of s is equal to V by R into 1 divided by S plus R by L. So if you take Laplace inverse, so V by R into e power minus R by L into t. So which is your current equation. So I of t is equal to V by R e power minus R by L into t. So if you substitute t is equal to L divided by R, so final equation it is V divided by R e power minus 1. So we already know that e power minus 1 is 0.3678. So if we simplify it, so we will be getting 0.368 VR. For decaying case, time constant for RL series is defined as the time required to reach 36.8 of its maximum value. So if you draw the curve, you could able to see that it is steady state after 5 tau. We have a problem. Find the expression of a transient current at time t is equal to 5 seconds having the resistance 2 ohms and inductance of 5 Henry after the switch is closed. Assume zero initial condition. So supply voltage potential rise is equal to summation of all your potential drops. So VR plus VL. So R into I of t plus L into di by dt which is equal to V. So R is equal to 2 and L is equal to 5. So if we take Laplace on both sides, so 2 into I of s plus 5 into s into I of s minus initial condition is already 0. So we just leave that, which is equal to 20 divided by s. If we simplify this, so I of s is equal to 20 divided by s into 5s plus 2. So if we simplify this, your current equation becomes I of t which is equal to 4 minus 4 into e power minus 0.4 t after taking Laplace. So if you take 4 outside, it's 1 minus e power minus 0.4 into t, which is your current equation. If you put this value in the graph, we could able to see that after 12 seconds, it is reaching the steady state value. From 0 time to 12 seconds, it is having the transient period. You will see the voltage across the resistance when the switch is closed. So VR is the voltage which is equal to R into I of t. So your R is already 2. So totally it is 8 into 1 minus e power minus 0.4 into t. So if you substitute this and plot the waveform, we could able to see that. So it starts from 0 and again goes to 12 seconds to become the steady state value. So this blue line represents voltage across resistance. This dotted red line shows the steady state voltage at 8 voltage and initial voltage is 0, which is represented by green color. So next we'll voltage across the inductor when switch is closed. So we already know that, so it's differentiate with respect to t. So we will be getting VL of t is equal to L into di by dt. So if we differentiate that, so we will be getting 1.6 e power minus 0.4 into t. So it's 1.6 into 8, 5, we will be getting 8 e power minus 0.4 into t. So if you plot this, it is decreasing from 8 voltage to 0 voltage. Since it is 8 into e power minus 0.4 into t, so blue lines represents the voltage across the inductor which is slowly decreasing. So at the 12 seconds we could able to see that it's 0. Then green line represents the initial voltage of 8 voltage and dotted red line represents initial voltage at 0.08. Then when switch is open, so you can be able to see that it is called as decaying RL circuits. So current starts to decrease. So it is 4 into e power minus 0.4 t. So it could be able to store only 1% of its initial current, that is 0.04 amps. So the current is decreasing from 4 amps to 0 amps after 12 seconds. We will see the voltage across the resistance when switch is open after 12 seconds. So it is 8 into e power minus 0.4 t. So we could be able to see that the voltage is decreasing. Likewise, when switch is open at the inductor, we could be able to see that again it is moving from minus 8 to 0. After 12 seconds, it is getting 0. When question is being said that after switch is closed at 5 seconds, what will be the value? So it is t is equal to 5 seconds. So if you simplify that, you will be getting 3.46. So it reaches at 3.46 amps